Okay, so in this problem, we have an airplane pilot sets a compass on the aircraft to go due west and maintain an airspeed of 220 kilometers per hour. So that's what this is showing here at the top. So there's this line that says 220 kilometers per hour, and then the arrow is moving to the left. So that's the west. So the airplane is going to supposedly to the west at a velocity of 220 kilometers per hour. However, they noticed that after half an hour, and this is on my screen right here, they noticed that after half an hour has elapsed, actually what happened is the plane is 120 kilometers west and 20 kilometers south. So what's happening, of course, is that, yeah, the airplane pilot set the compass and all the instruments correctly, but there is a wind outside and it's blowing the airplane. And so what we want to, and so it's blowing the airplane off course. And so what we want to do is we want to figure out how fast the wind is blowing, so the airplane pilot can like counteract it. Okay, so we know the velocity of the airplane, which is 220 kilometers per hour west. Well, that's what was set. Now we want to figure out where the plane actually is. Where the plane actually is 120 kilometers west and 20 kilometers south. But we need a velocity though, and as you may remember, velocity is equal to distance over time, and so the distance for example in the west direction is 120 kilometers west, and the time is half an hour, or 0.5. Okay. And so obviously you can just like multiply 120 times 2, and you could do 120 divided by 0.5, or you could do 120 times 2. And if you do that, you get 240 kilometers per hour, and that's in the west direction, and it would be 40 kilometers per hour in the south direction. Okay, so let's go ahead and write that vector down. So maybe I'll change it to that, and we'll go something like that. This isn't to scale, so. All right, so here we have this vector here, and maybe I'll just sort of just do this just so we can see the components of it. So the x component is, I'm gonna make this up here a negative, just showing that we're going in the negative direction for with this black line, and then and then the red one, we're gonna go negative 240 kilometers per hour. That's the velocity there, and then down is negative 40 kilometers per hour. Okay, so we have two vectors. We have this black vector and we have the red vector. Now, what does the black vector actually represent? Well, the black vector actually represents the velocity of the plane relative to the Earth. No, relative to the air. So the plane doesn't really know about the Earth. It really knows about the air. It's moving relative to the air, okay? So this is a relative velocity problem, or what they call a Galilean transform problem, okay? So the black here, this black vector, is the velocity of the plane relative not to the Earth, but to the air. So when the pilot sets the instruments, it's not like quote unquote looking at the Earth. It's compared to the air around it, okay? So that's the velocity of the plane relative to the air. Now this red vector is the velocity of the plane relative to the Earth, because for example the pilot looks down, let's say, and goes, oh, this is where we actually are over the Earth, and so we actually went 240 kilometers to the west and 40 kilometers down, so that's where we actually are on the Earth. And so, but how did we get there? Well, like I said, the air pushed the airplane. So that is, let's change to a blue vector. That's this one. So this blue vector is the velocity of the air relative to the Earth. Relative to the Earth. So the air is moving, right? But it's moving relative to the Earth. And so it's that air that's pushing the airplane. And so what we want to do is we want to figure out. So we know the velocity of the plane relative to the air. It's negative 220 kilometers per hour. And we know the velocity of the plane relative to the Earth. It's negative 240 and 40, negative 40. But we don't know the velocity of the air relative to the Earth, and that's what we want to find out. So how would you do that? Well, obviously this is just a linear equation. I mean, a linear algebra problem, right? Where you have some vectors, two vectors, and you want to find a third vector, okay? So let's do some like algebra. So if I have some linear algebra. So if I have the vector of, maybe I'll actually write it in the same color, just so it's more obvious. So I have the vector of the plane relative to Earth is equal to what? Well, it's equal to the black vector, which is the velocity of the plane relative to the air, plus this blue vector, which is the velocity of the air relative to Earth. So you could see, if you canceled the when you say v, velocity of the plane over air relative to air plus the velocity of air relative to Earth, if you canceled out the a, you would end up with p over e, or the velocity of the plane relative to the Earth. Okay. Now what do I want to find out is once again, I know the red vector and I know the black vector, but I don't know the blue one. So we'll just do a little bit of algebra here, and then after we rearrange some terms, you end up with the velocity of the air versus the Earth is equal to the velocity of the plane relative to the Earth minus the velocity of the plane relative to the air. Okay, so we just sort of rearranged some of the items here in this equation, and now we have what we're looking for. Okay, so now all we have to do is just some subtraction. So what is the velocity of the plane relative to Earth? That's the red one. So I'm going to write this in vector notation. So I'm going to go negative 240, comma, negative 40. That's that one. That's that vector. And then we're going to subtract it, right? Look at our problem. We're going to subtract it from what? From the black vector, which is negative 220. Negative 220 and 0. It's not going down, okay? And so if you do that, you end up with so it's negative 240. So the negative and the negative cancel out, so that it ends up being negative 240 and a positive 220, and so that ends up being I should make this blue since that's what it is. It ends up being a negative 40, like that, comma, this is 20. That's my bad. Yeah, negative 240 and a positive 220 ends up being a negative 20. And then negative 40 and 0, of course, is negative 40. Right? So this is the velocity of the air relative to the Earth. So that blue vector is that. It's negative 20 in the x direction, and then negative 40 in the y direction. That's great. But that doesn't actually tell you how fast it's going. And so if you want to know how fast it's going, obviously you'd want to take the velocity. Let's say I want to know what its velocity is. You did it equal to the square root of, say, negative 20 squared plus negative 40 squared, and I'm going to actually pull up my calculator real quick and do that and find out what that is. Okay, and so yeah, so the velocity, so this is a vector, right? So this is basically the length or the magnitude of the vector is 44.72. 44.72. And then everything here is in kilometers and hours, so it's kilometers per hour. So that's the actual speed of the plane. Oh, sorry, let me back up. That's the actual speed of the air, okay? But not its direction. So if I want its actual direction, what I might want to do is let me draw a coordinate system like this, and obviously the origin is right there in the center, and I want to put this vector right here and draw it. Okay, so I want to go negative 20 in x. Let's say here, and then negative 40 in y. Let's just sort of say something like that. Okay, so there's our vector, negative 20, negative 40, and let's say I want to find this angle here, and I'll just call it alpha. Okay. So what I can do is I can say the tangent of alpha is equal to, of course, it's opposite over adjacent, right? So it's negative 40 over negative 20. That ends up being just 2, right? And so now you have the tangent of alpha equals 2. And now, how do I actually find, what I'm looking for is I'm looking for alpha. So if I take the inverse tangent, so let's just write this down. If I do the inverse tangent, tangent inverse of tangent of alpha equals, and I have to do it for both sides, right? Because it's an equation. If I do the inverse tangent, that's inverse tangent of 2, right? You'll end up with alpha equals the inverse tangent of 2. And if you do that, you'll get 63 degrees. Okay, so it turns out that the air is actually moving at 44.72 kilometers per hour at 63 degrees south of west. So yeah, you can think of it as like so. So you're basically, it's going west, but it's pushing down south. That angle there. Okay, and so once you know this velocity that the air is pushing the airplane, then instead of being off track, you could actually counteract it by changing the controls of the airplane so that you wouldn't be off track, right? Okay, so this was an example of relative velocities using, like I said, a Galilean velocity transform, and hopefully it was useful. All right, that's it. Thanks.